Ever wonder how something as small as a microchip can power your entire computer? Or how laptops are built from almost nothing? Today, we're pulling back the curtain on the invisible tech running your world. From sand turned into silicon to the blinking cursor on your screen, this is how microchips and computers are really made. Every step, every machine, and every detail broken down in a way that finally makes sense. Stick around till the end. You won't just understand how it works. You'll never look at your laptop the same way again. A revolution etched in silicon. In the late 1950s, electronics took a bold leap. What started as bulky, room-sized computers suddenly faced a future where entire systems could be shrunk down to fit in your hand. This was the moment the microchip was born. It wasn't just a new invention. It was a full-blown revolution in how we build, use, and even imagine technology. Two names are central to this story: Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. Working independently, they both discovered a way to build entire electronic circuits on a single piece of material. It was Kilby who showed the world the first working integrated circuit in 1958. As he once said, "What we didn't realize then was that the integrated circuit would reduce the cost of electronics by a factor of 1,000,000. And that's exactly what happened. This innovation kicked off what we now call the digital age. Every advance that followed, personal computers, mobile phones, the internet, even smart toasters, can trace its roots back to this tiny rectangle of etched silicon. And with that came the need to make them smaller, faster, and cheaper. This drive to miniaturize is captured best by Moore's Law, a prediction made by Intel co-founder Gordon Moore in 1965. He believed the number of transistors on a chip would double every 2 years, and for decades that prediction held true. Why do microchips matter so much? Because they're invisible engines of modern life. They're inside your TV, your debit card, your car, even your washing machine. You may not see them, but they're doing a lot of the thinking for the devices we use every day. And it all started with a handful of ideas, a silicon wafer, and a lot of vision. But before these circuits can think for us, they have to be made, starting with the most unlikely of raw materials: sand. The digital gold mine from sand. It may surprise you, but one of the most powerful materials in technology comes from something we find on beaches. That's right, silicon, the core material in microchips, comes from sand. But not just any sand. It has to be silica-rich sand, refined until it's 99.999% pure. The process begins with this special sand being melted at over 1,400 degrees Celsius and slowly turned into a single crystal, what's called an ingot. This ingot is shaped like a large solid cylinder, almost like a giant metallic candle. The crystal structure is important. It ensures the material conducts electricity in a precise and controlled way. Once the ingot is formed, it's carefully sliced into wafers, thin, shiny discs no thicker than a coin. These wafers will eventually become the base of microchips. Why use silicon at all? Because it's a semiconductor. That means it can act like a conductor or an insulator, depending on how we treat it. And that's the secret sauce in all electronic circuits. Add a tiny bit of something like phosphorus or boron, and suddenly we can control how current flows. Silicon isn't just common, it's the second most abundant element on Earth after oxygen. And yet the silicon used in chips is anything but ordinary. It has to be almost perfect. Just one impurity atom for every 10 million silicon atoms. As one engineer once said, making chips is easy if you don't care whether they work or not. But of course we do. And that's why this process starts with such incredible precision. Now that we have our base material, the next step is figuring out how to etch billions of circuits onto a wafer that's barely wider than a cookie. Blueprint of a microchip. Before any chip is made, it's designed, and that's where the invisible magic happens. At first glance, a microchip looks like a piece of black plastic. But beneath that surface lies an intricate maze of billions of tiny switches called transistors, all working together like a microscopic city. The blueprint for this city starts on a computer. Engineers use specialized design software to lay out how the chip will work, what tasks it'll perform, how the electricity will move through it, and what each transistor needs to do. This virtual model can take months or even years to perfect. Once the design is ready, it's transferred onto something called a photo mask, basically a high-tech stencil. That contains the chip's pattern. This mask will guide the lasers and light beams that carve the chip's features into silicon. But it's not just about design. The environment has to be spotless. These chips are so sensitive that even a single speck of dust can destroy them. That's why they're built in clean rooms, where air is filtered constantly and workers wear full-body suits to avoid contamination. And in modern designs, chips don't just spread out, they stack up. That's right, 3D chip architecture is now common, with circuits layered on top of each other to pack more power into less space. We're not building cities, one chip designer joked. We're building skyscrapers you need a microscope to see. And now it's time to move from the drawing board to the real thing, starting with light, layers, and some of the most precise tools in the world. Light, etching, and atom-level engineering. Inside a clean room, everything is tightly controlled. Air pressure, temperature, humidity, and most importantly, dust. It's here that the real construction of the microchip begins. First, a photoresist layer, a light-sensitive coating, is applied to the wafer. Then, using an exposure tool called a stepper, ultraviolet light is projected through the photomask onto the wafer. Wherever the light hits, it changes the chemical makeup of the photoresist. Think of it like developing a photo, but for a chip. Next comes etching, a process where plasma gas carefully removes the exposed material, carving out pathways just tens of nanometers wide. That's smaller than a virus. The unexposed areas remain protected, shaping the intricate design of the chip. Then comes doping, where selected atoms, like phosphorus or boron, are fired into the wafer using ion beams. These atoms change how electricity moves through different parts of the chip, letting engineers fine-tune its behavior at the atomic level. All of this happens in dozens of stages. Layers are built up, etched, stripped, polished, and tested, each step getting us closer to a fully formed chip. As one technician put it, we're doing surgery on crystals, at a level where even atoms have addresses. After all that work, we have something that looks like a shiny disk full of tiny rectangles. But we're not done yet. Now we need to cut these up and bring them to life, from wafers to functional brains. Once the wafer is finished, it holds dozens, sometimes thousands, of tiny chips. But right now, they're just sitting there, side by side. The next step is to separate them with a process called scribing and sawing. Precision tools slice along thin grooves, leaving a gap called the scribe line, which helps prevent damage during cutting. Before they're packaged, each chip is tested. Special circuits are built into the scribe lines to check if the chips work properly. These test zones are then discarded during the final cut. The working chips are now ready for packaging, the part you actually see in everyday electronics. Each chip is placed into a small casing and connected to a set of terminals so it can communicate with the outside world. This stage is crucial. If the chip isn't properly bonded, it won't function at all. To finish, the surface of each chip is polished and clean, removing any final residue. Quality control teams use powerful microscopes to make sure everything is perfect. As one inspector noted, you don't see your mistakes until someone else's computer crashes. And now these tiny brains are ready to be placed into motherboards, phones, cars, and yes, even laptops. Which brings us to the next chapter, how a computer's core, the motherboard, is brought to life, powering the modern world. Now that we've created these tiny yet powerful microchips, it's time to see where they go. Spoiler, the answer is just about everywhere. Microchips are the silent workers inside nearly every electronic device you use. From your smartphone to your car keys, from your credit card to your TV remote, they all rely on chips to think, respond, and connect. It's amazing to consider how something so small can play such a massive role in modern life. There are even different types of chips for different jobs. Some handle memory, others handle processing, and many do both. Take your phone, for example. It contains microchips that process your calls, manage your camera, store your photos, and connect you to the internet. Each of these functions is made possible by a specialized chip. carefully designed and embedded into the device. But it doesn't stop at gadgets. Microchips are also at the heart of electric vehicles, trends, wind turbines, and solar panels. These aren't just everyday electronics. They're high-power systems that demand robust, heat-resistant semiconductors. These chips must handle enormous electrical loads while staying cool, fast, and reliable. This is why thermal management becomes crucial. Inside a high-performance chip, temperatures can soar. Engineers have to design cooling systems, tiny fans, heat sinks, and special packaging that keep them from frying themselves. And while today's chips are powerful, the future is even more exciting. Researchers are building chips designed for artificial intelligence, quantum computing, and even brain-like processing. They're also exploring new materials beyond silicon, because as efficient as it is, silicon is reaching its physical limits. As one AI developer put it, the chip is the modern-day engine. It's just not noisy and greasy. It's quiet and smart. So, now that the brain is built, where does it go? The next step in our journey is assembling the command center of every computer, the motherboard. From board to brain, think of the motherboard as the city infrastructure that connects everything together. It's the main printed circuit board, or PCB, that routes signals between the chip, memory, graphics, ports, and power. Without it, the computer is just a pile of parts. It starts with a green board coated in thin copper traces like tiny roads. Machines place a stencil over this board and apply solder paste in just the right spots. This paste will later bond components to the board. A camera checks everything to ensure the paste is precisely where it should be. Even a small smear or misalignment could mean a bad connection. Then comes a high-speed assembly line where robotic arms place components, tiny resistors, capacitors, and chips, onto the paste-covered board. These machines are insanely fast and accurate, placing up to 150 parts in under 30 seconds. Once the components are in place, the entire board goes through a reflow oven. This melts the solder paste and fuses each component to the board like baking a pizza, but this pizza is checked under a microscope, literally. After cooling down, inspection cameras double-check everything. Are all the components there? Are they in the right place? Are the connections clean? If it passes, the motherboard is ready for action. If the chip is the brain, one engineer said, then the motherboard is the nervous system. And with that nervous system fully connected, we shift focus to the part you actually see when you open a laptop, the screen. The eyes and ears. The top half of a laptop, called the panel kit, is more than just a screen. It includes the LCD, the webcam, microphones, Wi-Fi antennas, and even the hinges that let you open and close the laptop. It begins with technicians carefully prepping the LCD screen, often placing a protective film to prevent scratches. This screen is delicate, and just like the microchips inside, even a fingerprint could compromise its clarity. A cable is connected that will allow the screen to talk to the motherboard later on. Then the webcam and microphones are added. These are essential for video calls, recordings, and voice commands. They're installed into a small plastic frame that will sit above the screen. Next, engineers embed wireless antennas into the panel casing. These handle Wi-Fi and Bluetooth signals, and they must be placed precisely to ensure strong, consistent performance. The screen is then enclosed in a layered cover. Hinges are attached on either side, small mechanical parts that make a big difference. These hinges must be strong enough to hold the screen at any angle, but smooth enough to open with one hand. Finally, a metal frame is pressed around the edge of the screen, sealing everything in place. It gives the panel a finished look and protects the delicate electronics inside. As one technician said, "This is the part the user stares at every day. It's gotta be perfect." With the top half complete, it's time to move to the bottom half of the laptop, where sound, input, and cooling all come together. Building the base. The bottom half of the laptop is where most of the action happens. Here you'll find the speakers, touchpad, keyboard, and most importantly, the motherboard, now ready to be installed. Technicians begin by mounting the speakers, aligning them inside sound chambers that enhance audio clarity. These aren't just any speakers. They're engineered to make a small laptop sound as full as possible. Next is the touchpad, the smooth surface you use instead of a mouse. It's carefully placed into the top cover, aligned so your clicks and swipes feel natural and responsive. Then comes the motherboard. Remember the one we baked earlier? It's brought back and fitted into the base. Technicians secure it with screws and clips, making sure it connects cleanly to all ports, fans, and cables. Speaking of fans, modern laptops, especially gaming ones, use dual fan systems to manage heat. These fans are placed above the hottest parts of the motherboard and vent out through the sides or back. Every screw, every bracket must be snug and secure. Once everything's installed, a cooling calibration is done. Engineers ensure that airflow is smooth, temperatures are balanced, and no part of the system will overheat under stress. Cooling is the unsung hero of performance, a designer once said. Without it, the smartest chip in the world would melt down in seconds. With the base structure in place, it's time to add power and memory, the things that make the laptop come alive. The laptop's internal storage and fuel. Inside every laptop lies a delicate balance between speed and stamina. That's where memory and power come into play. The process starts with cleaning the connectors on the motherboard. Even a bit of oil or dust can cause a bad connection, so technicians use solvent and compressed air to get them perfectly clean. It may seem tedious, but this step is critical. Then it's time to install RAM, the laptop's short-term memory. This is where active programs and files are stored temporarily. Alongside the RAM goes the SSD, or solid-state drive, which acts as the computer's long-term storage. It's what holds your operating system, files, photos, and games. Next, a wireless module is added to enable Wi-Fi and Bluetooth connectivity. It slides into place with a click and is secured with tiny screws. Antennas from the top panel connect here, giving the laptop full signal strength. The last major piece? The battery. It's usually flat and wide, fitting snugly into a dedicated slot. Gaming laptops often use larger batteries, simply because their powerful chips and fans draw more power. Cables are tucked neatly, fastened with clips or adhesive to avoid movement. Any loose wire can cause problems later on, so neatness here is a matter of performance, not just looks. As one battery engineer put it, no matter how powerful your laptop is, it's useless if it can't stay alive. And with that, the laptop has all the pieces it needs to boot up and run. All that's left now is the finishing touch, the keyboard, and a final round of tests before it ships out. Finalizing the laptop. With the internal parts in place, we now turn to the piece you'll interact with the most, the keyboard. It might look simple from the outside, but installing it is a precise and delicate process. The keyboard must line up exactly with the top cover, not just for looks, but for comfort and function. A misaligned key or loose connection can lead to problems down the road. After fitting the keyboard into its slot, manufacturers use laser etching to mark information such as part numbers and manufacturing codes. It's a quick but critical step, ensuring each device is properly tracked from the factory to your hands. Now comes one of the final hurdles: testing. Every laptop goes through function checks. Each key, port, and input is verified to be working properly. Next, a durability test ensures the keyboard can take repeated use, especially on gaming models where aggressive typing is common. Technicians also inspect the screen and lighting, making sure color is uniform and there are no flickering pixels or brightness issues. As one QA inspector put it, people see the keyboard and screen first. If those aren't perfect, nothing else matters. With testing complete, the laptop is nearly ready to leave the factory. But before it ships, it must survive a few more challenges on the test floor. Quality control before it ships. Every finished laptop is only as good as the testing behind it. That's why it moves next to the test floor, a space filled with machines, monitors, and human inspectors who double-check every aspect of performance. Here, laptops are powered on and run through a full round of automated diagnostics. Everything from graphics rendering to USB ports is tested under load. If the device includes special features like virtual reality, those too are tested to ensure they work smoothly right out of the box. Some tests are tougher than what you'd experience in real life. The idea is simple. If it survives here, it'll thrive in your hands. After testing, the devices go through a final visual check to ensure there are no scratches, loose panels, or cosmetic defects. Then they're carefully boxed up, labeled, and moved to logistics, where they're prepped for worldwide distribution. As one warehouse supervisor put it, until it passes the test floor, it's not a computer, it's just a collection of parts. But once it does, it becomes something more, a complete machine ready to connect, create, and compute. Still, the story doesn't end here. In fact, we're just beginning to glimpse what's next. Shrinking sizes, growing impact. The story of how computers are made is a fascinating one, but the future, that's where things really get interesting. For decades, we followed Moore's law, doubling chip power every 2 years. That pace is slowing, but innovation isn't. Engineers are now developing chips designed in specifically for artificial intelligence, machine learning, and even simulations of how the human brain works. These aren't just computers, they're becoming thinking tools. At the same time, we're seeing the rise of modular and green computing, devices that are easier to repair, upgrade, and recycle, materials that are safer for the planet, and designs that use less energy without sacrificing performance. Even size is being reimagined, with the power of a full computer now fitting into phones, watches, and even glasses. The definition of a computer is changing. As one futurist said, the most powerful computer is the one you don't notice. It just works wherever you are. From grains of sand to silicon brains, from robotic arms to global shipments, this is how modern computers are made. And as technology keeps advancing, one thing is certain, we're only scratching the surface. And that's how microchips and computers are made, from end to screen. If you learned something new or just found the process fascinating, give us a like and hit that subscribe button. Got questions or thoughts? Drop them in the comments. We'd love to hear from you. Thanks for watching, and stay curious.